Kano Christian Michael. I'm a student in mathematical modeling. I'm from Cameroon. My project is started studying malaria control, data analysis approach for the intervention in Yaoundé. The prevalence of malaria in Sub-Saharan Africa has fallen significantly over the last decade, particularly in such urban areas such as Yaoundé, Cameroon, mainly to the industry adoption of vector control. However, this notable progress has come up against a formidable road, and many persistent problems continue to hamper malaria control effort. It is this diversity of distribution of malaria in time and space that motivates us to conduct a spatial-temporal analysis while evaluating the impact of certain factors in its transmission. We can illustrate the spatial degeneracy of malaria, distribution of malaria by this map. In this map, we can see that we have several different color points. The color indicates the prevalence of the village. We have a purple color, for example, who is the village who the prevalence is lower, prevalent between 0 and 55%, and we have a high village malaria prevalence, which is represented by the yellow points. Our project aims to respond to critical needs by exploiting existing data on malaria and environment combined with intervention. This objective can be rewarded in two specific objectives. The first one is assess the impact of environmental variables and well control strategy on malaria transmission and predict outcome. And the second is optimizing the deployment of intervention. We choose generalized additive model to conduct our method. The GAM is the very interesting tool for studying a behavior of certain factors on study variable. It is particularly useful when the relationship is suspected to be non-linear. More generally, GAM modeling of a handle variable y can have the following structure given by question 1. In this equation, UE is the expectation of response variable ye. F1, F2, and F3 are a univariate simulating function. Here we use a splitting function. F4 is a bivariate one. S1, S2, S4, S3, S4, and S5 are covariant in dataset used to explain a variable ye. They are correct explanatory variable. We will use cubic spin basic to interpret our data. Cubic spin basic interpretation will generally allow us to approximate smooth function underlying the dataset better than linear spin interpolation. The construction of cubic spin can give by equation 2 xt and xt plus 1 is the node obtained by discretize the variable x like you can see with this figure. X0 are the minimum of the variable and x5 are the maximum of the variable. We discretize the variable xi to have the node x0, s1, s2, s3, and s4. We can illustrate the construction of spin cubic like this. The curve and interpolate the data. But this interpolation is not optimal because when we collect data, we have a several error. An estimation reflects that if we interpret data, and in addition with error estimation, we apply the error of collected data. Instead to interpret, we opt to adjusting or fighting data. Is why we choose curve fighting spin. We want to estimate a curve that meets two objectives. The first objective is get as close as possible to the point in our data set. The second one is consider the general variation of a local variation in the variability. That two objectives are still contradictory, but the question is to find a best compromise to satisfy that two objectives. So to do it, we will give the penalty criteria by equation 2. So in the equation, we add some penalty to adjusted data. To satisfy the two expressions we have a parameter, and we have introduced the parameter to estimate. To facilitate the parameter estimation process, it will be necessary to express our univariate solution function like equation 4. Beta in this equation is a vector of parameter to be estimated, and beta k are small function created by a basis function created by spin, and function created by the cubic basis spin in dimension Q. To have the form 4, we want to rewrite our equation 2 like equation 5, where WE is equal to S of without observation YE. We can see YE can be given like a function. Now we talk about the bivariate smoothing function. Alors, so we will not detail the construction of bivariate smoothing function, but we will use two approaches to construct a bivariate smoothing function. We choose simple segregation for variables who are same scale, longitude and latitude who are same scale. We can choose simple smooth function, and tensor produce smooth function when the variables are not in the same scale. After construct the split function and the univariate split function and bivariate split function, we can propose the model like this. G of UE, the G of UE, ET, is a loop of linear function in the expectation of the response. I zone E, I time T. Alpha denote the intercept. Intercept means some value at the beginning. And ET is the size of the population at risk in district E, I time T, and introduced as an offset to adjust monthly malaria data by population. The FI lat long is used to incorporate spatial dependence effect of data. The spatial interaction of spatial or seasonal effects are incorporated using a tensor product of smooth function given by FEC log lan mon. And the function of T parameter FSC log lat long here is a tensor product smoothing function of annually varying coefficient of the marginal spatial smooth. The FIXE is a smooth function of environmental overhead and are modeled using simple regression speed or split cubic regression. Our model will allow us to identify the covariates that have significant impact of the spatio-temporal variability of incidence of case. because if we want to target intervention, we want to know which space or which time the prevalence is high and low. The second aspect is establish the contribution of spatial temporal effect on the variability of malaria transmission using different zones of the region study. Thank you for your attention.